part of this is I'm going to show actually too few pictures, but I do have a couple of pictures, and this is one of my favorites. I'm curious, and already our cameraman said that he grew up in the Philadelphia area. Anybody recognize this picture, or does it look familiar for areas that they grew up in? And anybody want to venture a guess of where we are here and what I'm trying to show with a pretty bad picture? I'm not a very good photographer. Any thoughts about where this is? Huh? The Heinz Refuge. Actually, really similar, really similar environment to the Heinz Refuge, a little bit further upstream than that. Yeah. I don't know Taylor's Nature Preserve. In Cinnaminson. Okay, so similarly, like the Heinz Reserve, freshwater, a wetland with spattered ox, so similar guess, but...
I can't place the hill, though.
Yeah, right, the hill and the house. So all of this, what I think is extraordinary is that this is a photo that was taken just a couple falls ago, and this is a photo that we wouldn't have been able to take 50 years ago because these fish wouldn't be seen there. This is actually right in the heart of kind of the urban corridor. This is in Camden city limits. This is on Newton Creek. So I'm in Camden, about a half mile from the Delaware River, and we're in the fall, and we were testing out a paddling tour, and on the way back, we were a little bit late. It took a little bit longer, as things often do. Sun is starting to set, so we're really trying to book and get back to our cars. And then the water around us erupted with baby shad, right? So these are young shad that had either been hatched here in the Tidal River in the Tidal Estuary or had been hatched further upstream. And here in the fall, they were thriving. I mean, there's a video, and if anybody's interested in seeing the video, I have it up on a Google Drive. They are erupting all around us. And so this is Newton Creek. Do you know Newton Creek? Reverend Evers Park. This is down near, pretty close to where the Walt Whitman Bridge is, so it's a little bit further downstream. But right, this is similar to like what you might see in a national wildlife refuge, like Tinicum, right? Like the Heinz Refuge. But this is actually, what's amazing is that this is now possible right in our most urban streams, right in Camden, right in Philadelphia, in Wilmington areas. And this wasn't possible 50 years ago. And so it's a really extraordinary restoration. But one of the big things I want to emphasize is the job is not done. People recognized back in 1967 in particular that they were going to be ambitious and they were going to target restoring dissolved oxygen back then, but they were going to have to make compromises. It was going to be a little bit too expensive to try for the most expensive things. It was a political decision ultimately about how much to invest, and they said, hey, let's shoot for halfway or a little bit better than halfway. Let's get there. We've actually overshot that, and now we see things like American shad now spawning in the river, even though that was actually more than people were expecting back in the 1960s.
Is that a fish I see?
Yeah, that's right. That's a little baby shad, and then each of these ripples are other shad that have just jumped right in that. So it's like pop, 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 pop. It's like almost like popcorn popping. It was just amazing to see that. And you can see this in a number of places up and down the Delaware River, and it's part of the reason that Delaware is so wonderful is that because it has no dams on it, we have all these migratory fish like shad, like striped bass, like sturgeon that move up and down. And so it really is an extraordinary river and one of the species that we can celebrate. And so to see them thriving like this, and not just thriving up in the Poconos or the Catskill Mountains, but to see them thriving, right here in the areas that used to be most polluted 50 years ago, right in Philadelphia, right in Camden, right in these urban areas, I think is really extraordinary. It's, again, part of the history, but it also, I would argue, is part of the future because there are things that we can do. They're not crazy. They're not, super advanced. They're not, space-age technology. They are actually conventional things that we can do now to make it so that all fish, all organisms that want to use these tidal river habitats, to use the estuary, actually have enough oxygen to live and thrive. So that's where I want to go. Let me provide a little bit of an outline for kind of the structure of what I want to talk about today. I first want to start with a little bit of the basics for this tidal system. I am not historically an estuarine ecologist, so I didn't do all of my research in these tidal river systems where freshwater and saltwater mix in these brackish systems. And so this was a learning experience for me over the last 15 years. about this tidal system. So I want to kind of lay the foundation by talking a little bit about the structure of the estuary. Then I want to go into the history of how bad things were and what was done to actually try to make that progress so that we can now see shad in the estuary. But then in particular, I want to emphasize on the future. What really is possible using conventional technology in an investment in areas that really have seen too little investment. I would argue that part of the reason that we're still talking about a future and that the fact that oxygen hasn't been restored is that this isn't the Chesapeake Bay, right? There are not million-dollar homes sitting on the edge of this part of the estuary. And so you don't have the constituencies. You don't have the people that are saying, hey, wait a minute, right? You know, this is Clean Water Act. We are almost 50 years now after the Clean Water Act. We should have done this a long time ago. I think that that is part of the story and part of the reason that we're still talking about the need to finish the restoration of dissolved oxygen in the Delaware Estuary. So that's where I want to go. Hopefully, I sometimes talk pretty fast, right? And I get pretty excited. I'm an excitable person. But please, if I'm going too fast, feel free to slow me down, stop, ask questions. I'm happy to talk about these things. And then certainly we have lunch afterwards. So if we want to have a more detailed and an in-depth conversation about any of these things, or if anybody wants any references, I can actually email you some of the papers that go into this history even more. And even better because I didn't write those papers, so they'll probably be more articulate than I'll be. Anyway, let me give first that introduction. The Delaware Estuary, oftentimes when I think of an estuary, I think of things that have salt water, that have brackish water. What's different about the Delaware Estuary is that it is not entirely a freshwater system, but the freshwater system is a really big part of it, right? A lot of the port facilities in and around Philadelphia and Camden are in a freshwater zone. The freshwater tidal river actually starts up here at Trenton, New Jersey. So this is a landform showing kind of the elevation across the estuary, Cape May and Cape Henlopen, so Cape May, New Jersey, and Cape Henlopen, Delaware down here. And this is actually 133 miles of tidal influence with still a 10-foot tide up here at Trenton, New Jersey. Really extraordinary, really a high energy system. You still see every day the tide twice a day go up and down 10 feet. So really big, high energy system. And more of a high energy system than some of the other estuaries that people might be familiar with. Higher energy than the Barnegat Bay, higher energy than the Chesapeake Bay. The tidal regimes there are a lot narrower, and that changes the whole dynamics of the system. The freshwater zone extends from River Mile 133 up here, and I'll talk a little bit more about river miles on the next couple of slides, all the way down through the Philadelphia-Camden region around here. And then actually the freshwater zone can extend to and below the Delaware state line. So when we're talking about the Hines National Wildlife Refuge, right, that is primarily a freshwater. You sometimes can get brackish water in a low water year that starts to work its way up. But sometimes, particularly in 2018, we had a ton of water. That freshwater line, that salt line, can move actually well down past Wilmington. And so we start to talk about the transition zone from Delaware further down. When I mentioned this is a high energy system with a 10-foot tide range up at Trenton, part of the reason that's important is that we don't get something called stratification in this estuary. And so I'm going to go back and forth between kind of waving my hands a little bit and then talking with some technical terms. Hopefully I will explain those technical terms. If I don't explain them well enough, feel free to slow me down and ask for clarification. But this stratification actually turns out to be really important in terms of how an estuary functions, particularly with human impacts to that system. So the Chesapeake Bay, part of the reason that people are really focused on nutrients in the Chesapeake Bay is it's a lower energy system, and so the Chesapeake Bay operates a little bit like a lake, where the upper water doesn't mix with the deeper water, right? You don't have this high energy system turning it all over again, and so if you have high nutrients in the Chesapeake Bay, you can get these huge algal blooms in that upper layer. That algae then die, they go to the bottom, that bottom water is not mixing, and so now that bottom water cooks. All of those that extra dead algae starts to decompose, and you use up all the oxygen in the lower waters. The Delaware system is not like that. Because of this 10-foot tide range, about 6-foot tide range in Philadelphia, 10 foot further up, we don't get stratification. We don't get different layers of water. We don't get an upper layer that is kind of always exposed to light and a deeper layer that isn't exposed to light. Instead, we actually mix that water bank to bank and top to bottom, and it's not a perfect mixing. Sometimes you can see salt water is a little bit heavier, so you can see a little bit of saltier water on the bottom than at the top, but generally speaking, it is a relatively well-mixed system, and so that means that we have different types of dynamics. You don't get a lot of algae up in that upper top layer, that epilimnion in the system, that then can die and decompose in the bottom. That algae are actually mixed every day up to the top, down to the bottom. And because of that high energy, we tend to have lower light penetration. There's more sediment that is stirred up in our estuary because of that energy, particularly with the tides. You can actually see differences in terms of the water clarity in the estuary depending on what tide you're at, right? If you're actually at high tide or low tide and the velocities are starting to slow down, a lot of that sediment starts to fall out of the system, right? And you get a little bit of extra clarity. But then as the tides are really moving, 3, 4, 5 miles an hour, you are actually re-entraining that sediment, and there's actually low light penetration. So if you're an algal cell and you're trying to use nutrients, it's a very different system than you would see over here in Barnegat Bay, or than you would see over in the Chesapeake Bay. So kind of interesting. Another thing that I won't talk a lot about is that one of the things that we're blessed with in this system is tons of fringing marshes. And of course, these are under threat with sea level rise, with some of the energy in the system. A lot of these salt marshes are eroding, and there are great groups like the Partnership for the Delaware Estuary that are looking at ways to eliminate that regression of those salt marshes. But we have lost most of our freshwater tidal marshes. The Hines National Wildlife Refuge is one of them. The Rancocas Creek has really good freshwater marshes. The Crosswicks Creek's up near Bordertown. There's some really good freshwater marshes. But a lot of those freshwater marshes, unfortunately, have been lost. I am going to show a fair number of slides today that talk about river mile, or have river mile on one of the axes, or talk about a single place in the estuary. And so I do want to give a quick orientation to river miles. River miles are measured from the Atlantic Ocean, so between the capes, Cape Henlopen and Cape May, that's river mile 0. We then get up to about river mile 50, and that is considered Delaware Bay. That's an official designation just below the Salem Nuclear Power Plant and Artificial Island, and a little bit below the Chesapeake and Delaware Canal is where Delaware Bay starts, so that's about river mile 50. We get up to Wilmington at about river mile 70, and then the Delaware State Line at river mile 79. You then get into Chester, Philadelphia, and Camden, the Philadelphia Airport. And in addition to river miles, I'm going to talk a little bit about zones of the estuary. So the Delaware Bay is considered Zone 6. That transition zone where the fresh water meets the salt water is Zone 5 that covers Wilmington. Zone 4 covers the Philadelphia Airport and the lower parts of the Philadelphia city limits, and that extends up to river mile 95. So river mile 95 is a little bit below the Walt Whitman Bridge. And then, and the next slide I'll show this, Zone 3 then goes from Philadelphia up to the upper city limits in northeast Philadelphia to near where the Rancocas Creek comes in on the New Jersey side. And then again, up at Trenton is river mile 133. So some of the graphs I'll show, I'll start at river mile 133 and we'll go down. Oftentimes I won't be presenting data for the Delaware Bay. I don't have as much data. It's not quite the focus with this question of dissolved oxygen. But in particular, river mile 100, it's somewhat convenient that it's a nice round number. There was a dissolved oxygen sensor that was placed in the river back in the early 1960s. And this is really pretty extraordinary because it is still even challenging. And we saw this with the presentation this morning with the turbidity sensors, right? It is no trivial matter to install a sensor that measures turbidity, that measures pH, dissolved oxygen continuously. And so the fact that they were able to do this back in the 1960s and put a DO sensor in essentially under the Ben Franklin Bridge, if people know Philadelphia, the connection to Philadelphia and Camden, there is a wealth of data going back all the way to the 1960s where they were measuring dissolved oxygen essentially every hour of every day, year-round initially, and now they don't do it as much in winter because we always know that dissolved oxygen is going to be fine in winter, and the sensors get damaged in winter. But almost every day going back to the 1960s, we know what the dissolved oxygen was under the Ben Franklin Bridge. So we have a very rich data source in which to be able to tell this story of the history of dissolved oxygen. So again, under the Ben Franklin Bridge, river mile 100, that's where I'm going to present a lot of data for. The last thing I want to mention is the transition between freshwater, brackish water, and salt water. Most of what I'm going to talk about today is up in the freshwater zones. The freshwater zones were the areas that were most heavily impacted by the gross pollution from industry, from populations, from the wastewater treatment plants. Philadelphia, Camden, Gloucester County, Delaware County regional wastewater treatment plants, Wilmington in the brackish water zone, but Wilmington is really kind of at the lower end of the really severe zone. So it starts out as fresh. Zone 2 from Trenton down to Philadelphia is freshwater. Zone 3, again, down through Philadelphia, this is a true freshwater. Only during the drought of record during the 1960s did the salt line, and this was a multi-year drought in the mid-1960s, did the salt line actually start to march up towards Philadelphia. So this is, Zone 3 is truly a freshwater zone. Zone 4 is mostly freshwater, 9 months, 10 months out of the year, maybe sometimes 12 months out of the year. The salt sometimes does get up above the Delaware state line, depending on what you think of as the salt threshold between freshwater and brackish water. And then we get into the big transition zone from freshwater up near the Delaware state line to brackish water around Wilmington to pretty salty water in that zone. Yeah, question?
Can you define
Yeah, right. So that's actually a term that I didn't know before I came into this. So they talk about kind of 3 haline regimes. Oligohaline is kind of like oligotrophic when people are talking about eutrophication, meaning very low salt. So it's not quite fresh water. You can get a little bit of salt mixed in, but oligohaline is that just beginning to mix a little bit of salt in with the fresh water. Then you get into mesohaline conditions. So zone 5 is typically fresh, but the lower parts of it can actually be a mesohaline, and then polyhaline. And I'm not quite sure why they call it poly. But anyway, polyhaline is the higher saltwater condition. So yeah, I guess lots of like multiple versions. But anyway, so yeah, oligohaline, mesohaline, polyhaline. So that's a little bit of the kind of the background for the Delaware Estuary. Again, we're going to mostly focus on the freshwater zones of that. And I'm not going to, even though I'm an ecologist and a biologist, I'm mostly going to be talking about the dissolved oxygen itself. I will present some slides for some of the key species, but it is important to think about the aquatic life in this system, right? That the reason to restore dissolved oxygen isn't for its own sake, but of course there are all kinds of organisms, right? From worms and microbes up to clams, different kinds of freshwater mussels and different insects and shrimp and things, or shrimp-like creatures that live in the estuary, up to the fish and the eels, some of which are migratory. And one of the points I wanted to make here is that there's also a replacement depending on what kind of salt regime you're in. This is a picture of mostly what things look like in the freshwater zone. Again, I'm going to focus on the freshwater. But as you get down into that brackish water, into that oligohaline or mesohaline, you will get a replacement of these freshwater clams with other kinds of brackish water clams. Similarly, you get replacement of other fish that are specialized. This is a bay anchovy, so this actually is not a freshwater organism most of the time. It sometimes pokes its nose up into the freshwater zone, but it's mostly in the brackish water zone. And so you get replacements depending on which zone you are in. But part of the point here is that the ecosystem is wonderfully complex. There are multiple species in every one of these groups, from the aquatic plants and the types of phytoplankton that are living in the water column, to the zooplankton, to the clams, to the other kinds of invertebrates, from little worms and midges to aquatic insects like caddisflies, and shrimp-like creatures like amphipods or scuds, and all of those feeding this amazing ecosystem. And this is really what we're trying to protect with the restoration of dissolved oxygen. So, quick orientation to the estuary. Now let's talk about the history of dissolved oxygen problems. And this really is a very long history. This is a graph. On the x-axis here is time, going back to the early 1900s for the first reliable data points. I've actually modified this from a professor at the University of Delaware. But the city of Philadelphia in 1912 and 1914, they were looking at their water quality problems, where they were getting their source water. And as they measured summer conditions right there in the Philadelphia region, they were measuring oxygen concentrations. This is in kind of scientific notation, micromolars, but they were measuring oxygen concentrations in the range of 1 to 2 milligrams per liter. Even 100 years ago, right, before a lot of the big population boom in Philadelphia, before World War II, they were already measuring hypoxic conditions, very low, stressful oxygen conditions in summertime back in 1912 and 1914. Certainly things then got worse as we look at time, and this dotted line, I should have given an orientation. This dotted line is that standard. I mentioned in 1967 there was a compromise position. That's what this dotted line means. And see if I can get out of that. This is the problem with a smartboard.
Don't touch the screen.
Right, exactly. That's what I was worried about. So the dotted line, and what I'm going to talk about is that dotted line being 3.5 as a concentration of oxygen, milligrams per liter of oxygen is that dotted line, and it's equivalent to just over 200 micromolars there. But oxygen conditions really became stressful after World War II. Things got really, really bad, right? Beginning in the 1940s, 1950s, and then we have a lot of that data because partly of those oxygen sensors that were installed in the 1960s. We have really good data in the 1960s to show how bad things were. But things went from bad 100 years ago to worse in the middle part of the last century. And then in the 1960s, when people really started to get serious about this, things were bad. And I want to illustrate this. I want to talk about just how stressful it would be. It's like holding your breath, right? Yeah, sure, we can all hold our breath for 10 seconds, 15 seconds. Me and my kids, when we're driving through tunnels, one of the tricks is like, all right, can we hold our breath all the way through the tunnel, right? And I try not to do it as the driver, thinking like, well, if I don't make it, it's kind of worse than if they don't make it. But it's kind of the question that if you're one of those freshwater mussels, or you're a shrimp, or you're one of those fish in the estuary, how long can you hold your breath? And things were so bad in the 40s, 50s, and 60s, and maybe even 100 years ago, that there was no way to hold your breath, right? You would entirely eliminate all of the living organisms from this Delaware Estuary system every year, because this is a pretty typical pattern of what things look like. This is the year 1967. I mentioned there were some severe droughts in the 1960s. 1967 was as they were coming out of the multi-year drought, so it's a pretty typical year. There are 3 different lines here, and these are data from the Ben Franklin Bridge, again, River Mile 100, right, so between Philadelphia and Camden. 3 lines, the dark blue line is the maximum, the green line is the daily average concentration of oxygen, and the oh, there I go, I shouldn't have touched it. The light blue line is the minimum dissolved oxygen. Our scale here now is back to what I'm more used to seeing is milligrams per liter of oxygen. Milligrams per liter is a pretty common concentration for a lot of things when we're talking about concentrations of things in water. And the standard now is at 3.5 milligrams per liter. But what we saw then in 1967, and what we saw pretty much every year, probably from the 40s through the 50s, so in terms of talk about holding your breath, right? Can you hold your breath for 3 decades? Pretty hard to do. But this is what we would see every year, is that oxygen concentrations winter would be okay, would be 8-10 milligrams per liter, but sometime in April or May or the beginning of June, all of a sudden they would start to crash, right? And they would get down to 0 or near 0, not for a couple of days, not for a week or 2, but for the whole month of June, for the whole month of July. Oh yeah, maybe you see a couple of days where oxygen bumps in. And then the month of August, and then the month of September, the month of October. Sometimes it wouldn't be until November or December, after things are actually, as ice forming is in the river, before oxygen would actually start to recover, right? So we're talking about 5 to 6 months out of every year that oxygen, there would essentially be no oxygen under the Ben Franklin Bridge, and for a zone about 10 to 20 miles of the Delaware Estuary, a complete lack of oxygen, bank to bank. Again, this is a high energy system, well mixed, right? A truly dead river, right? Really pretty extraordinary. And I didn't appreciate that. I think a lot of people didn't know how bad this was. And it's remarkable because these data are freely available by the U.S. Geological Survey. So if anybody wants to take a look at this, it's pretty amazing to look at. In terms of along the length of the Delaware Estuary then, starting upstream at River Mile 133, the head of tide in Trenton, again, our zone 2, 3, 4, 5, and 6, we only have part of zone 6 here, so I don't really talk about the Delaware Bay very much. And then oxygen concentration still in milligrams per liter here. And the main thing I want to show is oxygen starts off up in Trenton. Things back in the 1960s weren't perfect from Trenton upstream. There were problems, right? There was industry, there were wastewater treatment plants, there was a lack of wastewater treatment at municipal facilities, but things generally were better from Trenton upstream than they were in the tidal part of the river. And so oxygen concentrations usually started out pretty good, and so that's what this black line indicates. Started out okay. There was actually a little sag around Bristol, right? So there was enough of raw waste going into the river that between the Burlington and Bristol Bridge, there was something called the Bristol Sag. Oxygen bumped up again. But then as you got towards Philadelphia and Camden, oxygen concentrations totally tanked and went to zero or near zero and stayed zero down through the Philadelphia airport, almost zero all the way down to the Delaware state line. And still down at River Mile 70 near Wilmington, you were still in true hypoxia conditions. So from River Mile 70 up to almost River Mile 110, you were in this zone of stressful oxygen conditions of hypoxia. So 40 miles out of a 133-mile length estuary, we're talking about a third of the length of this entire system that has either no oxygen or very little oxygen. And again, that lack of oxygen wasn't a couple of weeks, right? Could you hold your breath? Could you put your nose up in a little tributary and survive? No, we're talking about 4, 5, 6 months out of every year. So really horrific conditions historically.
Is that like a running average?
This is actually, it's a little bit hard to define what this is. It is represented in some graphs as a minimum of averages. So it would be a daily average and what is kind of the lower part of that distribution, some of the worst cases of that. But as that last graph showed you, it was regularly at zero. So for Ben Franklin Bridge right here at River Mile 100, it actually is a little bit worse than this graph shows, that on a regular basis, most days out of the entire summer and most days out of September and October, you were all the way down at zero. So it's somewhat of a typical condition, but it's a little bit hard. I actually can't recreate that line with my own data. It was based on some old modeling results. So 100 years of hypoxia, again, based on City of Philadelphia data going back 100 years. We expect that the worst conditions began in the 1940s. The data are a little bit sparse, but certainly by the 1960s, things were really bad. Total absence of oxygen for typically 5 months every year and extending for about 30%. About a third of the estuary was hypoxic. And then, of course, there are biological effects. What did this mean? We don't have a lot of data on all the different organisms that were living in there, right? From freshwater mussels and shrimp. Yeah, question.
Was the 5 months in the winter or the summer? I missed that part.
Sorry, it's just in the summer. The winter, this is actually kind of an interesting property, is that oxygen dissolves better in cold water than it does in warm water. And so it's easier to get oxygen into the river in the winter months during cold periods. So it's just easier to have higher oxygen concentrations in winter. And that's part of the reason trout streams have trout in them, is they're colder and so oxygen dissolves better. So all of these problems were summer problems extending sometimes into the winter. So they would extend certainly into the fall. They would go into September, October, and November. But generally speaking, that lack of oxygen would be at its worst in the summer months. Yeah?
What's the difference between hypoxia and anoxia?
So hypoxia means stressful oxygen conditions, but you're not quite at zero. Anoxia means an absence of oxygen. So anoxia would be that 10 to 20 mile zone, like around the Ben Franklin Bridge, down to the Walt Whitman Bridge, down to the Philadelphia airport. So that's the zone where essentially almost nothing can live, right? Whereas the hypoxia, some tolerant organisms, things like mummichugs, can actually tolerate 1 or 2 milligrams per liter. There aren't a lot of things that can do it, but there are a few things that can.
You're saying that the Delaware, this area was experiencing 100 years of hypoxia.
That's right.
Starting in 1912-ish.
Yeah, that's right. At least 1912, right? And some speculation, how much before then, how much after that. That's right. So the one thing I want to illustrate in terms of the biological response is the American shad. And this is an iconic fish. It was really important historically. There's a book written about it called The Founding Fish, about its importance. Some people are nodding their heads and acknowledging it. Really important going back hundreds of years. Important recreationally, important commercially. And what we saw were there were problems going back, and this is a data source from Lambertville, New Jersey. This is a family that's been had a commercial fishery there in Lambertville for essentially 100 years now, and so it's a very consistent data source. What we are missing in this graph is that shad catches back in the 1800s, back in the 1700s were higher than this, so there were some high numbers back then, But even by the 1920s, there were still shad making it up past Lambertville, past New Hope, up past Easton, and then up into the Poconos and the Catskills. But the numbers were already really low. When we get to those really horrible conditions in the 1940s and 50s, there were essentially zero. There were years that the Lambertville seine haul, they would still pull the nets every year, but they wouldn't catch a single shad, for multiple years in a row. There was a couple of weird years. I'm not going to talk about these weird years, and there's a lot of speculation about why there's some weird years in the 1960s, where all of a sudden they shot back up and then they collapsed back down to zero again. But what you start to see is the rebuilding of those shad eventually, and so that's where I want to get to. But to illustrate how bad things were is that these are the shad that were trying to make it above the DO block in Philadelphia and Camden, right? These are the shad who are saying, look, I can't spawn down there near Philadelphia. There is a neighborhood in Philadelphia, Fishtown, right? And that is actually named for the shad fisheries that used to be there in Fishtown, right? But by the early 1900s, right, there were no shad still spawning in that area. They had to move upstream. These were the shad that were adapted to say, okay, I know there's some clean water further upstream. I'm just going to try to make it through there. And what had happened with this collapse is that the shad do stage in March and April, and there is enough oxygen in the estuary in March and April for the adult shad to get in there and to get up past Lambertville. But what we saw in the 1960s, right, there was no oxygen in the fall, and so those young shad had no ability to get back out, right? The shad have to move back out to the ocean every year before winter comes. And what would happen is that those few that were successfully spawning upriver, their young shad, those young of the years, that picture from Camden that I showed in that first slide, they would all die on their way back out to the river. And that's why we have a complete collapse of the shad fishery in the 40s, 50s, and 60s. So really big biological responses. Death of just about everything. Shad are just one species for which there would be a loss of life, but that would be true with a lot of different species. Yeah?
In terms of river miles, what was the historic shad spawning area?
Oh, that I don't know that precisely. Certainly around Fishtown, right? There was good, strong spawning, and there's still actually there is now spawning again around the Fishtown area. I've seen people say that shad spawning would extend actually down past the airport, down to the whole Hines-Tinicum National Wildlife Refuge, and maybe even some spawning down towards the Delaware state line and even further downstream. The salt line has moved up historically as we have dredged the river and made it deeper and better for shipping. We've moved that salt line up, and so historically, shad probably had a broader spawning area in the Tidal River than they do now. Now it looks like it is mostly from Philadelphia upstream, although certainly there's the potential to restore that down towards the Philadelphia airport and then down towards the Hines Wildlife Refuge. Yeah, that's right, because they are freshwater spawner, but because that still is freshwater, there is the potential to spawn down there. But there were multiple spawning zones historically for shad in the river. So next, I've used up about half my time, maybe a little bit over half my time, so I want to talk about the restoration. I might blow through these slides even faster than I was blowing through some of the first slides, because I want to get to the idea of the future and what we need to do. I want to put it in a little bit of context with the various efforts. At the federal level, at the national level, there was this really important act in 1948 that we now know as the Clean Water Act, but it was called the Federal Water Pollution Control Act. So that was first passed in 1948. That started to say in the 1940s, hey, we got to start to deal with some of these water quality problems. It wasn't terribly effective for the tidal Delaware River. There were revisions in 1965 that I want to come back to, not major revisions. The big overhaul was 1972. What we now know as the Clean Water Act wasn't actually called that in 1972, but it was a rewrite of the Federal Water Pollution Control Act in 1972, and that implemented a lot of the programs, a lot of the standards, a lot of the requirements, a lot of the funding mechanisms to actually lead to improvements were the big changes in 1972, so important for that timeline. And then it actually became the Clean Water Act in 1977 when they called the revisions the Clean Water Act of 1977. In terms of the big changes in the Delaware River around Philadelphia, Camden to Wilmington, there was a series of efforts by this interstate commission beginning in the 1930s. 1938, this acronym INCADEL started. Wasn't terribly effective, right? We didn't see good oxygen concentrations in the 40s and 50s. In 1961, the subsequent agency called the Delaware River Basin Commission, an agency for which I worked for 10 years, was created in 1961. The federal government got more involved in the 1950s. And then there are these series of events. These 4 events, I would say, are at the core of the restoration of the Delaware River and of the dissolved oxygen. And these 4 things are still relevant today as we think about finishing that restoration job. The first thing was a modeling study by the U.S. Public Health Service, 1961 to 1966. I'll talk a little bit more about that. It included a computer model of water quality in the Delaware Estuary. You can imagine the computers weren't very sophisticated in the 1960s. It's really amazing that that model turned out to be pretty darn good at predicting what we needed to do and what would happen if we did it. And then this is the compromise. 1967, the Delaware River Basin Commission, again, partly based on those revisions to the Federal Water Pollution Control Act in 1965. Those revisions in 1965 said, hey, you can actually set these standards that are actually applicable across state lines. So you can set interstate water quality standards. They said that was okay in 1965. Hey, you've got this new water quality agency, the Delaware River Basin Commission. Why don't we try to actually implement those? So they did that. 1967, the first true water quality standards for the tidal Delaware River. And then in 1968, 1 year later, they said, okay, now we need to put the river on a diet. We need to actually put in pollution controls, and we are going to allocate for individual facilities how much of certain types of pollutants you're allowed to discharge into the Delaware River. So 67, 68 are really big dates for this restoration. And then 1972, so right, the federal response is about 5 years later. 1972, the big thing that we now call the Clean Water Act comes into play. So it wasn't actually the first thing. Some people attribute the restoration of dissolved oxygen in the Delaware Estuary to the Clean Water Act. Actually, some of the most significant things happened before what we now call the Clean Water Act was in place. Again, I'm going to move a little bit fast through here. That modeling study I mentioned was called the Delaware Estuary Comprehensive Study, the DEC study, big modeling and data collection. Big budget, $1.2 million back in the 1960s. So, right, really big budget project, serious investment. And it resulted through a series of committees in a set of recommendations as high as 4.5 milligrams per liter dissolved oxygen, that some of the fisheries groups were saying, hey, we can really restore this estuary. Others, mostly folks who had a vested interest in not spending very much money, saying, no, that's going to be hard to get 4.5. 2 or 2.5 would be just fine, and we get some of those uses back. And in the end, it was a compromise that the Delaware River Basin Commission, as having the 4 governors as its commissioners, as well as a federal representative, right, is a political entity, and they said, all right, we're going to pick a middle number, and they picked a middle number of 3.5 milligrams per liter. And given that there was no oxygen in the estuary, right, for many months out of every year, this was pretty darn ambitious, right? To say that we can go from 0 up to 3.5 was actually a pretty ambitious goal. So I think that they actually was a pretty bold step back in 1967 to say that we can do this and we have the ability to do it. But one thing that's important to emphasize about that compromise in 1967 is that they knew that they were making a compromise. They said, essentially what we're going to try to do by hitting 3.5 milligrams per liter is we're going to try to keep adult fish alive. In water quality standards language, we're going for maintenance instead of maintenance and propagation. Propagation meaning we're going to allow those fish and those shrimp and those insects to actually be able to reproduce in the estuary. They're saying, hey, that's just a little too much. That's either too expensive or technologically it's not feasible. That's too far. So we're going to allow those shad to migrate through the estuary on up, but we're really not going to try to get those shad to actually be spawning in the estuary again. A compromise position. Question?
Do the water quality standards in 1967 include other like goals besides dissolved oxygen, or was this kind of like?
They actually include, they are actually a full, not quite a full, a pretty good list. pH standards, temperature standards, dissolved oxygen. So yes, it wasn't just about dissolved oxygen. The big move, though, that was going to have an impact on the kind of economic situation was the dissolved oxygen standard, because it also involved that diet, that waste load allocation. And so probably the most controversial part of this, and a lot of the debate around those standards was with dissolved oxygen. But no, I can actually share with you what those 1967 regulations look like if you're interested, and can show you that. So in terms of then the diet, there were 2 different components to the main pollutants that were causing the dissolved oxygen problems, CBOD and NBOD. And actually, let me pause and talk really briefly about that. So these are wastewater parameters, and if there's any wastewater engineers in the room, they probably can explain this even better than I. I'm going to simplify it a little bit. Mainly think about those two types of waste coming out of a pipe at a municipal facility or an industrial facility as carbon-based oxygen demand or nitrogen-based oxygen demand. Both of these are essentially food for microorganisms, for aerobic microorganisms, so they need oxygen, but there's some very specialized bacteria, Nitrosomonas and Nitrobacter, that can actually feed on nitrogen, right? So not using nitrogen as a nutrient source, but actually nitrogen, particularly reduced forms of nitrogen, as a food source. So that is the NBOD component. But then most of the microbes in the estuary are going to be feeding on the carbon component of it. So that's your CBOD, your carbon-based oxygen demand, carbon as food. So those are the two big components that they were looking at in the 1960s, and they said, okay, the CBOD, the carbon, is the bigger source. It's about 1 million pounds per day of this carbon that is demanding oxygen demanding carbonaceous biochemical oxygen demand. Whereas the NBOD, the nitrogen food, is around 600,000 pounds per day. So about 2/5 versus 3/5 of the problem. They said the carbon was a little bit easier to treat at wastewater treatment plants. We're going to go after that. It's the bigger source. So that's what we're going to put a diet. And we're going to try to reduce that 1 million pounds per day down to 300,000 pounds per day. But we're going to kick the can down the road for that nitrogen. We're going to say at some point in the future, it'll be easier technologically. We'll have the financial resources after we've dealt with it. Then we'll go someday and deal with that NBOD. So, of course, you're going to see where I'm going with this. That's what we have to do today. And this is similar to the graph that I showed you before. Trenton up here at River Mile 133, the Delaware Bay down here at River Mile 48. This dotted line are those conditions that I was saying were kind of typical in the 1960s. The rectangular black line are the water quality standards. So particularly in the Philadelphia down to Wilmington area, that standard is set at 3.5 milligrams per liter of dissolved oxygen. And then what's really interesting about this graph is this thin, smooth line here, which was saying that with that, sophisticated 1960s computer model, this is what they said they could get to by going from 1 million pounds per day down to 300,000 pounds per day. They said, yeah, we're still going to have a Bristol sag of dissolved oxygen. We're still going to have a dissolved oxygen sag in Philadelphia, Camden, down to Wilmington, but we think we can get oxygen above 3.5 milligrams per liter during summer. That's what they said they could do. Pretty amazing that this is a graph similar to the one before of what things look like now. This is a 10th percentile, so not kind of typical conditions, but kind of lower end conditions. And so again, starting out here at Trenton, things look good. We actually don't have a Bristol sag anymore. The oxygen conditions actually restored better in the upper part of the estuary, but still around Philadelphia, from the Ben Franklin Bridge to the Walt Whitman Bridge, that's the low point in the estuary now. But it looks amazingly like what they said they would get to with those models of the 1960s. So pretty amazing. And look at the difference between those graphs. Again, right, this is an amazing uplift in dissolved oxygen. And this now means that there are a lot of organisms that can now survive, that no longer have to hold their breath and can actually thrive in this estuary. And they really have actually exceeded their expectations. And we actually now have shad spawning again in Fishtown, right? They're actually spawed. If you take a sample during shad spawning season, you will find eggs and larvae of shad right there in Fishtown now. So pretty extraordinary, and they actually did better than they expected to do back in the 1960s.
The fish ladder that they installed around the aquarium, did that have any influence on it?
So the fish ladder is more about trying to spread the wealth around and trying to get shad and herring and other things like American eels up into more of the tributaries. So the Schuylkill River, they rebuilt the fish ladder there at Fairmount Waterworks. On the Cooper River, they got a fish ladder up the Cooper River. So that's more about trying to stabilize the populations by getting them to spawn, not just in the main river, but getting them to spawn in all the different tributaries too, where there are dams and things. So, yeah.
I know you said this already, but could you just concisely say what were the main reasons why the oxygen levels had plummeted in the Delaware?
Yeah, so it's all about those that CBOD and NBOD, that the both industrial facilities and municipal facilities like the city of Philadelphia were dumping their raw waste into the estuary, and that was food for microbes. So it's actually good that you asked that question, so I'm going to try to boil it down. That all that food for microbes meant that the bacteria were going gangbusters in the river, and these aren't bacteria that are harmful for humans, they're just bacteria that are decomposers. And so they were stripping the oxygen out of the water column because they were all or not all, but a lot of them were aerobic microorganisms, and so they were using up the oxygen as they were decomposing those wastes that were dumped into the river. And so we were just dumping so much food into the river that they were using up all the oxygen as they decomposed that food. Yeah. So again, restoration, right, bad conditions. This is just the month of July, again at Ben Franklin Bridge. Really bad conditions. You start to see a little bit of improvement in the 1970s, but you really start to see the improvement in the 1980s. Decent conditions through the 1990s. But one thing that I want to emphasize, and there's two numbers here. The 5.5 milligram per liter is the standard set by the state of Pennsylvania. 3.5 is the current standard. But you can see that over the last 20 to 30 years, we bop around, right? We sometimes have really good years. 2014 and 2015 were really extraordinarily good years. But then 2016, just a year later, all of a sudden we're back into a moderately stressful. We're above that 3.5 milligram per liter standard, but we're not in the clear. We are not to truly safe and healthy oxygen levels. Yeah.
So is it temperature that causes the fluctuation?
It's not temperature. There's a little bit. There is a relationship between temperature. Certainly, right. Oxygen has a harder time dissolving in warmer water. So in a warm summer, you might expect that, but we don't really see that clearly. Right. So a warm summer doesn't always correlate to these bad years. Sometimes in a cool year, you'll get a good DO summer, but sometimes in an average or a cool year, you'll actually get a bad summer. So there are modelers. There's actually some really fantastic modelers at the Delaware River Basin Commission now that are trying to answer that question. Why do we get bad years? And are building a much more sophisticated model as we speak, and are bringing in some other great modelers from outside to help them build that model. So it isn't. That's exactly what I ask myself, and a lot of good people ask themselves, like, all right, is there a quick relation that when we get hot summers, those are the years that we get the worst dissolved oxygen? It actually doesn't look like it's that simple. It looks like there's something weirder going on here, and we don't know the answer to that.
How are they monitoring the amount of CBOD?
Right, yeah. So
we know we're meeting the targets on CBD.
So this is actually, that's a good segue, because 2 points. That's related to the Clean Water Act. The requirements in both Delaware River Basin Commission permits and in the Clean Water Act is that you actually have to monitor what's coming out at the end of your pipe. So you have these effluent monitoring requirements at your discharge monitoring point, a certain point. And so they take a sample, sometimes multiple samples a day, you run that to a lab, and one of the parameters that they measure is their CBOD. They measure either just a straight total biochemical oxygen demand, carbon and nitrogen BOD, or they measure just the CBOD. And so they're measuring that on a regular basis, saying, and they actually measure what's coming into their plant because they have to show a % reduction also. So they're measuring all the nasty stuff that's coming in and hopefully the cleaner stuff that's going out. So it's part of their regular monitoring, and that's part of the national monitoring that's required under the Clean Water Act permits. And so that's also part of the reason I think that's a good segue. It's part of the reason we saw a delay, right? 1967 were those DRBC regulations, but part of the reason we didn't see an immediate rise in dissolved oxygen is it took the money and the power of the EPA to really build momentum, right? So DRBC can say, hey, everybody, you got to hit 3.5 and you have to start to clean up your waste, but where's the money? Where is the city of Philadelphia? Where is the city of Pottstown going to get the money to do that? When the Clean Water Act was authorized, primarily they started with grants. They just said, hey, if you build that plant, we will help you pay for that, straight out. Then it transitioned to loans. But there was federal assistance to get everybody to do that, and then you actually had the authority. So there were, and I'm not going to point names partly because I'm on video today, but there were places in this watershed where in the 70s and 80s, there were politicians who just said, I'm not building it. I'm not going to treat my waste. I'm just going to dump it in the river, and you can't make me do it. And EPA said, well, actually, no, there's this thing called the Clean Water Act, and yes, you actually are going to build it, but you have a 5 or 10 year court battle before you can actually make them do that, and then the timeline to actually build it. So it was the authority and the money of the Clean Water Act that really helped build momentum and really start to restore things and get above that 3.5 milligram per liter dissolved oxygen. So good conditions. I don't have a lot of time. Right now, I have 10 minutes till I go. So I'm going to blow through this pretty well, pretty quickly. Striped bass recovered. So 0 striped bass in 1980. A lot of people told the biologists there's no point in going out there and trying to collect striped bass, right? That's a dead estuary. So this is 1980, right? Almost 15 years after the 67 regulations were passed. They still said, don't even bother monitoring for striped bass. You crazy, right? Same thing with shad. 0 shad in the 1980s when the state of New Jersey was out looking for young shad, right? Total collapse. But then with that graph that I showed you earlier, beginning in the 70s and then through the 80s and into the early 1990s, the shad started to recover at Lambertville. Those fish were getting through, of course, but just as importantly, their young shad were making it back out to the ocean, and so you were building momentum and a good biological recovery. So ambitious goals set in 1967, a focus on carbon, the carbon food that was being dumped in the estuary, kicking the nitrogen can down the road. And so in 5 minutes or less, I'm going to talk about that nitrogen side of things, which is to say that despite the fact that there was no allocation for the nitrogen-based oxygen-demanding compounds, the nitrogen food, by all of these upgrades, by upgrading your wastewater treatment plant from primary treatment to secondary treatment, you're going to get some benefit. You're going to get some removal of that. And so the total load now is approximated at about 300,000 pounds per day, and they did a little bit better on the carbon side. The carbon side, they're probably more around 100,000 to 200,000 pounds per day. But that's to emphasize now that there is still this really big component in terms of the nitrogen-based food being dumped into the river that could be treated inside the wastewater treatment plant. In the estuary, you're still allowed to discharge at the end of your pipe, through that discharge monitoring, 35 milligrams per liter of ammonia. That's actually similar to how hot the ammonia is coming on into your plant, right? Oftentimes it's coming in at about 30 milligrams per liter. So you can discharge just as much ammonia at the end of your plant as is coming in. Pretty antiquated technology, and one of the only places in the country where you're allowed to do that is here in the Delaware Estuary. Here in Pottstown, no. You have to be discharging something like 1 milligram per liter of ammonia. And a big part of that is that this uses up oxygen in the receiving system. So people here in Pottstown aren't allowed to use up oxygen out here in the Schuylkill River. It's like, no. Use the oxygen inside your plant. Bubble oxygen through your plant. Hold that water long enough, and that way we're not depressing oxygen out here in the river. In Philadelphia, and again, this is where the overtones are about, all right, people don't really live along the river, or the people that live along the river, aren't very wealthy. It's not Annapolis, Maryland, with these beautiful houses and sailboats. There's no rush, right? That's expensive. Why make them do that in Philadelphia, right? What's the point of doing that? And it's like, wait a minute, we're talking 50 years after the Clean Water Act, right? This is standard, right? We should not be talking about a 35 milligram per liter standard at the end of pipe 50 years later, when this is conventional technology, when even not affluent places like Pottstown, right, like almost every town everywhere else in the Delaware watershed is required to do it, but the city of Philadelphia isn't required to do it. Camden County is not required to do it. Gloucester County is not required to do it. So pretty extraordinary. And a modeling study from the 1990s said that this is depressing dissolved oxygen by about 2 milligrams per liter, right? So that difference between that 3.5 milligram per liter standard that currently is there and that Pennsylvania standard of 5.5, right? It looks like, and DRBC is trying to evaluate this a little bit more carefully right now, it looks like that could be solved by just getting these treatment plants to upgrade that. And then the cast of characters, the city of Philadelphia's Southwest plant, in particular because partly they're handling all of the sludge down at that facility, they have really high ammonia. And so they are the biggest dog in this fight. And about 80% of their nitrogen that comes out of their plant is still coming out as ammonia. And a lot of the other facilities, not just Philadelphia, Wilmington, Camden, all the way up to Hamilton, up near Trenton, a lot of them are still discharging most of their nitrogen as ammonia. What I want to show is the possibility for uplift, right? This is how bad things were. This is where they are today. If we take and treat that ammonia and we use the oxygen inside a plant rather than using oxygen out in the estuary, this is what I've been working on some estimates, and this isn't the detailed modeling of DRBC, but our estimates based on an 80 to 85% saturation and treating that ammonia is that you can entirely eliminate this DO sag in the Philadelphia-Camden region, and you can stay above 6 milligrams per liter on almost every day of every year, right? And that this becomes relevant because there still are species like, we have 2 species of endangered sturgeon in the estuary, Atlantic sturgeon, who spawn down right in this zone of hypoxia, and then short-nosed sturgeon, and they spawn further upriver. They spawn from Trenton up to Lambertville area. So they're not as impacted by this. But the Atlantic sturgeon, if you look, and these are data from the state of Delaware, and then my own analysis of dissolved oxygen conditions, that even in the last 10 years, every summer that you have a bad summer where oxygen concentrations aren't very good, you essentially catch no young sturgeon that summer or that fall, right? A total collapse of the Atlantic sturgeon population. Again, an endangered species. As soon as you start to get to half or more than half of those 90 days in summer where oxygen concentrations are 6 milligrams per liter or higher, all of a sudden, correlationally, you get the best summers in terms of Atlantic sturgeon. So you have the possibility of a real biological response and perhaps even a restoration of an endangered species because these 2 species of sturgeon are particularly sensitive to low dissolved oxygen concentration. So there really is a possibility of improving dissolved oxygen. It's relatively straightforward, and it's using conventional technology. Again, there's a lot of talk about non-point source pollution, and there are plenty of places in our country where non-point source pollution really is the main driver for a lot of impairments in our streams. The tidal Delaware River around Philadelphia and Camden is not one of those places. That part of the river still has problem with what's coming out at the end of the pipe, partly because it's such an urban area with such dense populations of humans and such dense populations of industry. We still have problems with PCBs. We still have problems with perfluorinated compounds, something that other folks are talking about here, right? So the estuary is still dominated by point sources, and we have the possibility of restoring dissolved oxygen. What has worked in the past can work again in the future. It is conventional technology. It's being used right here in the town that we're in right now, in Pottstown, right? To use oxygen inside the plant to convert that ammonia, not an expensive treatment where we denitrify, but you convert that ammonia to more stable forms of nitrogen that are not food for microbes, and you actually could eliminate the DO sag that persists in the Camden and Philadelphia, and that has at the very least, overtones of an environmental justice issue. Why has this been an area that hasn't been cleaned up 50 years after the Clean Water Act? Why are people continuing to kick that can down the road? There was an effort in the 1980s and 1990s to try to do this, at least in part, and that fills out. And so we're continuing to have to fight that fight now in practically 2020. So it's possible to do. It's an exciting opportunity. I have additional publications if people are interested in reading it. In particular, this story is told really well by one of my precursor, a fellow who died, unfortunately, a couple of years ago named Dick Albert, who worked at the DRBC and then went to go work at the Delaware Riverkeeper Network. So really an extraordinary individual, and I'm happy to be following in Dick's footsteps. But he was a much better storyteller than me, so his publication, you guys might like to read it. But a bunch of other studies there. And it is now 12:30, and I have gone over. I appreciate the questions during the thing, and I'm happy to answer other questions either now or after people leave for lunch. But thank you for your time.